Hi, I'm Mark Barsamian. In this video, we'll be studying infinite limits and vertical asymptotes, and we'll be taking an analytic approach. That is to say that the function f will be given by a formula, not by a graph. Recall the limit notation that we've discussed in previous videos and the trends that that limit notation represents. We have this collection of symbols involving the limit. So for instance, this symbol represents the following trend. As x approaches the number c, the y values approach the number L and may actually equal L. And remember, that means that the graph is heading for the xy location, c comma L. And remember that that was something that we discussed in section 2.1 of the book. So all of these symbols in these cells of this table have to do with things that we discussed in section 2.1 of the book. Limits, if they existed, had to be real numbers, and they denoted the idea that the graph of the function was heading for some particular xy location. We also had symbols like the following. This is spoken: the limit as x approaches c from the left of f of x is infinity. And that is shorthand notation for the following trends. X is approaching some number c from the left, and the y values are growing more and more positive without bound. And that corresponds to the graphical behavior that the graph of f has a vertical asymptote with line equation x equals c, and the graph goes up along the left side of that asymptote. Now that kind of limit was the sort of thing that we discussed in section 2.2, limits that have an infinity symbol in their abbreviation. We had limits as x approaches some number and the y values are getting more and more positive or negative without bound. Those limits were what we call infinite limits, and they corresponded to vertical asymptotes. And we had limits where x is approaching infinity, and the y coordinates could be approaching some number or could be growing more and more positive without bound or more and more negative without bound. For our first example, we're going to use the function f of x equals 5 over the quantity x minus 7. We're supposed to find the function value and limits listed below and explain what they tell us about the graph of the function f of x. And we're supposed to use the terminology and notation of infinity where applicable. That is, concepts from section 2.2. All right, so let's do question A first. F of 7 does not exist. This tells us that there is no point on the graph with x equals 7. For question B, we're being asked to compute the limit as x approaches 7 from the left of f of x. That is, the limit as x approaches 7 of the quantity 5 divided by the quantity x minus 7. Now, let's remember how we would have done this using section 2.1 techniques. So we would have looked at the limit of the numerator, because this is a rational function. We would have found that the limit of the numerator was the number 5, and we would have used that theorem 2.1, which says that the limit of a constant is just the constant. Now, the limit of the denominator would be computed in the following way. We would have found that the limit of the denominator was the number 0, and the key step in that limit was using theorem 3, which says the limit of a polynomial function is just simply the same as computing the y value at the x value where you're supposed to be computing the limit. So the limit of the numerator is not 0, and the limit of the denominator is 0. Therefore, we know that the limit does not exist. The limit of the ratio does not exist, and that's using theorem 4. Now, the fact that the limit does not exist tells us that there's no limit in the sense of section 2.1. That is, there's no real number L that the y values are getting closer and closer to. But we're told to use the terminology and notation of infinity where applicable. That's concepts from section 2.2. So the question is, how should this limit be done using section 2.2 techniques? Well, remember the difference between section 2.1 and section 2.2 limit terminology and notation. In section 2.2, we have terminology and notation for abbreviating the descriptions of more kinds of trends in the x and y values of a function. To use section 2.2 terminology, we need to have more information about what the x values and the y values are doing in order to see if we can discern a trend. One way to do this is to make a table of x, y values. Well, so how should we populate the table? Well, we're being asked to find this limit, the limit as x approaches 7 from the left of f of x. Part of this symbol is this symbol, x arrow 7 superscript minus sign. This tells us that we need to investigate x values that have the following trend. X is getting closer and closer to 7, but less than 7. So we build a column of x values that are doing that, and we compute the corresponding y values for the second column. So here's our table. There's our list of x values that are getting closer and closer to 7, but less than 7. Now let's build the column of the corresponding y values. So we can see clearly the trend in the resulting y values. The y values are getting more and more negative without bound. And let's show that this behavior described in this question, or this sentence, is showing up in the table there. So for clarity, let's write a single sentence description that describes both the trend in the x values and the trend in the y values. As x is closer and closer to 7, but less than 7, the values of f of x get more and more negative without bound. Well, we recognize that this sentence description has an abbreviation in limit notation. This is spoken, the limit, as x approaches 7 from the left, of f of x is negative infinity. And that tells us the following about how the graph behaves. We know that the graph has a vertical asymptote with line equation x equals 7, and that the graph goes down along the left side of that asymptote. Now let's remind ourselves how we knew how to construct this sentence. First of all, this 7 shows up there when we describe the line equation. And the negative infinity shows up there when we said the word down. The graph goes down. And the word left shows up here when we describe the behavior of the graph going down along the left side of that asymptote. Remember what I mentioned in a previous video about this situation. In the Barnett book in section 2.2, the authors would write this symbol, but they would say in words that the limit does not exist. The reason they would do that was because using section 2.1 techniques, that is theorem 4, there was no limit in the sense of 2.1. Remember that a couple of pages ago. Using section 2.1 techniques, we found that the limit does not exist in the sense of section 2.1. So that's why the authors say that the limit does not exist. The limit does not exist in the sense of section 2.1. That is, there is no real number L that the y values are getting closer and closer to. But I don't like saying that the limit does not exist when in fact we know that the limit symbol is that. Saying that the limit does not exist obscures what we've learned about the function, and it does not convey that we've actually expanded our definition of what a limit can be. So in my videos, if I find this, then I will say this. In other words, if I find that the limit is infinity in the sense of section 2.2, that's a concept from section 2.2, then I'm going to say that the limit is infinity. That's using the full terminology of this expanded idea of limit from section 2.2. In question C, we're being asked to compute this limit. Now, let's again quickly observe what would happen if we were to use section 2.1 techniques. So the limit of f of x is the limit of this ratio, and it does not exist by theorem 4 of section 2.1. So this thinking that I've circled in green is what goes on here. That's how we reach the conclusion that the limit does not exist. But again, that's how we would have solved this problem in section 2.1 techniques. But we're supposed to use the terminology and notation of infinity. These are the techniques of section 2.2. So we are going to do what we did in the previous question. We're going to make a table of x, y values. In the current question, we have x arrow 7 plus. That is, x is approaching 7 from the right. So we have to build a table with a column of x values that are doing that, and then compute the corresponding y values for the second column. I'll start by building the column of x values. So there is my column of x values. They're getting closer and closer to 7, but greater than 7. Now we have to build the column of y values. Remember that y is computed by the formula 5 divided by the quantity x minus 7. We see a trend in the y values. The sentence summary is the following. When x gets closer and closer to 7, but greater than 7, the y values get more and more positive without bound. So this behavior, that the y values are getting more and more positive without bound, we saw that happening in that column of the table. This behavior, that x is getting closer and closer to 7, but greater than 7, was happening in that column of the table. The corresponding abbreviation in limit notation is this is spoken, the limit as x approaches 7 from the right of f of x is infinity. The corresponding graph behavior is that there is a vertical asymptote on the graph with a line equation x equals 7, and the graph goes up along the right side of that asymptote. And again, let's remember how we knew how to construct this sentence. This number 7 that x is approaching shows up in the sentence there. The fact that the graph goes up comes from the fact that the limit is infinity, so that tells us that the graph goes up. And finally, the idea that we're talking about the behavior on the right side of the asymptote came from this, x is approaching 7 from the right, so that's how we knew to put that word right in that spot. All right, now let's move on to question D. In question D, we're asked to find the two-sided limit. That's easy. The limit does not exist because the left and right limits don't match. Now I'd like to talk a little bit about some common invalid solution methods that I see in student solutions to problems about limits involving infinity. Most of the time, these solution methods, these invalid solution methods, give the incorrect answer. Sometimes they happen to give the correct answer. But regardless of whether they happen to give the correct answer or not, the solutions are invalid. So I'll present two of the most common invalid solutions to question B, C, and D that we did above. But notice that I did not solve the problem this way when we solved example 1. So here's the one common invalid solution. So notice that the first two solutions here gave the wrong answer. My solutions to B and C gave the wrong answer. We know that the correct answer to B is that the limit is negative infinity. And we know that the correct answer to C is that the limit is plus infinity. So the idea that the limit does not exist is just incorrect. So B and C are clearly incorrect solutions. Now, question D, this is the correct answer, but this solution method is invalid. The way that we know that this solution method is invalid is that it often gives the incorrect answer. So even though once in a while it might give the correct answer, it doesn't mean that it's valid. The whole thing is invalid. We also did not do this in our solution to questions B, C, and D. So notice that the answer to question B is incorrect. We know that the limit is, in fact, negative infinity. And we know that the answer to question D is incorrect. The limit is not infinity. The limit does not exist. Now, the answer to question C happens to be the correct answer, but the method is invalid. We know that the method is invalid because a lot of the times it gives the wrong answer. So all of these are invalid solutions. The general thing wrong with these invalid solutions is that they both involved plugging in a single number. And the thing is, the limit involves a trend. So you have to consider the trend in the y values in order to figure out what the limit is. For our second example, we're going to revisit a function that we studied in an earlier video about limits of rational functions. The function is this beast of a function, and we're supposed to find these function values and limits and explain what they tell us about the graph of the function. And we're supposed to use the terminology and notation of infinity, that is concepts from section 2.2. Now, remember that when computing y values at particular x values and when computing limits at particular x values, it's most convenient to use the factored form of the function. So we were given this function in two forms. It's most convenient to use the factored form. So the y value does not exist. Now we're supposed to say what that tells us about the graph. That tells us that there is no point on the graph with x equals 3. In question B, we're being asked to find this limit, the limit as x approaches 3 from the left of f of x. Now, remember how we would have done this using section 2.1 techniques. We found that the limit of the numerator was the following. We found that the limit of the numerator is the number -4. To do that, we used theorem 3. That is, we observed that the function we were taking the limit of, the numerator, is a polynomial, so we can just substitute in the x value. Now the limit of the denominator is found the same way. So the limit of the numerator is -4, which is not 0, and the limit of the denominator is 0. And so therefore we know that the limit does not exist. The limit of the ratio does not exist, using theorem 4. So the limit of f of x as x approaches 3 from the left in section 2.1 techniques does not exist. And that told us that there was no limit in the sense of section 2.1. That is, there is no real number L that the y values are getting closer and closer to. But in the current example, we're not told to do the limit using the techniques of section 2.1. We're supposed to use the notation in the terminology of infinity, if it's applicable. That's concepts from section 2.2. So how do we do that? Well, we can start by simplifying the limit and doing some canceling, but we must do it carefully and explain why we can do it. Here's how it goes. So if we start taking the limit, we are taking the limit of this expression, and in that expression there is an x minus 5 over x minus 5. Now we know something about that factor. We know that x is getting closer and closer to 3, so that tells us that x is not equal to 5. And so since x is not equal to 5, we know that x minus 5 is not equal to 0. And so we can cancel x minus 5 over x minus 5, which arrives us at this simpler limit expression. So there's that concept that is the most important concept of the first month of the course. When can we cancel terms and why can we cancel terms? So our original job of finding this difficult limit has been simplified to finding a simpler limit. So that's now our job. The limit of f of x is this simpler limit. So we are going to investigate this by making a table. So notice that part of this symbol is this. This tells us that we need to investigate x values that have this trend. So x is getting closer and closer to 3 and less than 3. So we build a column of x values that are doing that, and then we compute the corresponding y values for the second column. Here's the table. There's our list of x values that are getting closer and closer to 3, but less than 3. Now we have to build the corresponding y values. Now remember what those are. The y values that we're interested in are these. So notice there's a trend in the y values. The y values are getting more and more negative without bound. So here's the sentence summary. So the sentence summary reads, as x approaches 3 from the left, the y values get more and more negative without bound. So the trend in the y values we observe from that column of the table. The trend in the x values is in that column of the table. So recognize that that sentence description has the following abbreviation in limit notation. This is spoken, the limit as x approaches 3 from the left is negative infinity. And that tells us something about how the graph behaves. It tells us that there is a vertical asymptote. The vertical asymptote has line equation x equals 3, and along the left side of the asymptote, the graph is going down along the asymptote. All right, in question C, we're supposed to compute the limit from the right of f of x. So we will again start by simplifying the limit by doing some canceling, and we'll explain why we can do it. So first I'll write down the limit expression and then do the canceling. So the limit simplifies to this simpler limit as it did in question B. And the reason that we're able to cancel is, well, as in question B, we know that x is getting closer and closer to 3. So x is not 5. So since x is not 5, we know that x minus 5 is not 0. Since x minus 5 is not 0, we can cancel the expression x minus 5 over x minus 5. So we need to make a table of values to investigate this simpler limit. So we're going to need some x values. We need to have x values that have the following trend. X has to be getting closer and closer to 3, but greater than 3. So we have to build a column of x values that are doing that, and then compute the corresponding y values for the second column. So I'll do that table here. So there you see the list of x values that are getting closer and closer to 3, but greater than 3. And now we'll compute the corresponding y values. So notice that there's a trend in the resulting y values. The y values are getting more and more positive without bound. So here's the sentence summary. As x approaches 3 from the right, the y values get more and more positive without bound. So we observed this behavior in the y values, and we observed this behavior in the x values that we built. The corresponding abbreviation in limit notation is the following. This is spoken, the limit as x approaches 3 from the right of f of x is infinity. The corresponding graph behavior is that the graph of f of x has a vertical asymptote with line equation x equals 3, and on the right side of that vertical asymptote, the graph is going up along that asymptote. In question D, we're asked to find the two-sided limit. That's easy. The limit as x approaches 3 of f of x does not exist because the left and right limits don't match. That's the end of example 2. Let's compare the limits of our function, f of x, this rational function, using section 2.1 techniques versus using section 2.2 techniques. So using section 2.1 techniques, so in all three cases, the left limit, the right limit, and the two-sided limit, the limit does not exist if we use section 2.1 techniques, because theorem 4 tells us, since the limit of the numerator is not 0 and the limit of the denominator is 0, that the limit does not exist. Now, let's review our results from the example that we just did using section 2.2 techniques. We found the following. Using section 2.2 techniques, the limit from the left was negative infinity, the limit from the right was plus infinity, but the two-sided limit still does not exist. However, the two-sided limit does not exist for a different reason in section 2.2 than it did in section 2.1. In section 2.2, all three of the limits failed to exist by theorem 4. Using section 2.2 techniques, the reason the limit does not exist was not because of theorem 4, it's because the left and right limits don't match, so not because of theorem 4. So in section 2.2, when limits don't exist, it's not because of theorem 4, it's for some other reason. All right, that's the end of this video. Thank you.